cryptocurrencies. What's your current view on cryptos?
Well, so I've been in as an investor in crypto for quite a bit of time, actually. So I think I bought Bitcoin in 2014. I took my first 2 or 3 paychecks actually from the University of Washington, put it all into Bitcoin.
Wow.
So it was trading, oh man, I'm trying to remember what the price was, but I think it was around $400 when I got it. And then I got into Ethereum pretty early on as well. So I have a friend of mine from graduate school, was pretty early on into crypto, much earlier than me. And he kind of was one of these people who always had like kind of different ideas of the world, but I could tell that he kind of had this very good view of what was going to happen. And so I kind of trust his advice. So he was the one that said, hey, you might want to buy some Bitcoin, and hey, you might want to buy some Ethereum. So, I mean, I bought some, and I didn't do much for a long time. And then I really sort of 2020 started to look into everything that's being built on Ethereum with smart contracts. And it just blew my mind how much is being done, how they're just completely redoing the financial system. And so I'm completely sold. People think I'm crazy, but I would say I probably have 80% of my net worth in my Ethereum wallet. So I'm pretty gung-ho on crypto. I like it. I think
that's great. My son's actually president of a bank called Custodia, which will be the first or second bank in the US to be allowed to custody Bitcoin.
Oh, I just heard a podcast yesterday about how somebody there had actually tipped off the SEC and maybe some other regulators about things that were potentially going on at FTX far before FTX collapsed. And apparently, our regulators didn't do anything about it. And, so yeah, I'm aware of Custodia Bank.
Okay, cool. Well, it looks like we're getting to 6 o'clock. Zathra, are we ready to go?
Yes, we're ready to go. And just so you know, Matt, this is a webinar, so you may not see the participants, but they are there in the background.
Okay, all right.
Okay, so welcome everybody.
Sorry, one quick question. Do I need to pay attention? Do people type in their questions? Do I need to pay attention, or can they just interrupt it?
They can raise their hand and you can call on them, when you want to.
Okay, all right. Yeah.
And we'll monitor the chat as well, so we'll let you know if there are questions.
Oh, that'd be helpful, because I'll probably be staring at my slides and
okay.
not be paying attention. And feel free to just ignore and say somebody's got a question. I'll stop.
Okay, we'll do that. Thank you.
Okay, great. So let's get started. It's my great pleasure today to introduce Matt Lorig from the University of Washington, speaking on the semi-parametric replication of barrier-style claims on price and volatility. Matt has a really interesting background, which we had a chance to talk about before the call, including stints in Mexico City and Chile, and an early investor in Bitcoin. On the academic side, he's an associate professor at the Department of Applied Mathematics at UW. Prior to joining, he worked as a postdoc as scholar and lecturer at the Department of Operations Research and Financial Engineering, or ORFE, at Princeton. He holds a PhD in physics from the University of California, Santa Barbara. Professor Lorig has written papers on a variety of topics within financial mathematics, including implied volatility, optimal investment, robust replication of path-dependent claims, sports betting markets, technical analysis, and most recently, cryptocurrencies and decentralized finance. Please welcome me in joining Matt Lorig.
Thanks very much for the introduction. I sort of forgot that I had written on sports betting markets. That's something I need to get back to. So I think here, if I share my screen, it says somebody needs to enable screen sharing for me to do so. When I click share screen, it says,
yes, Zathra will take care of it. I think she might need to get James to.
Okay, no, let me help. Hold on 1 second. Deborah Priya, are you there?
Yes, I'm working on it. Just give me a second.
Okay, thank you. We have an IT tech on hand, and he'll make sure that you're able to share your screen.
Okay, I think you're good. You should be good now.
Yeah. Try it. Should be good. Let me give it a shot here. Screen, I'll share the whole screen and
Okay, there you go.
let me go to view and probably presentation would be good. All right, so everybody can see my screen now, right?
Yes.
Somebody give me a thumbs up. All right, great. So the title of my talk is sort of semi-parametric pricing and hedging barrier style claims on price and volatility. And before I tell you exactly what I mean by semi-parametric pricing and hedging, I think a good place to start is to sort of contrast it or talk about what I mean by parametric hedging. And so one second here, I'm actually covering up. I wonder if I can, oh good, I can move that thing down to the bottom there. So the parametric approach to pricing financial derivatives is sort of the standard way that we think about pricing financial derivatives, which is you start by writing down a parametric model for an underlying. So typically when I'm talking about an underlying, I'm thinking of a stock, and that's why I use the word, the letter S. But it could be an index, it could be an interest rate, something like that. And so typical models for stocks would be something like the Heston model or the Sabre model or an exponential Levy model. And so in order to specify the dynamics, you have, you have to say what particular parameters are. And so the way that you find those parameters is you calibrate your models to observable liquid call and put prices that are on the market. So you kind of have the sense that, well, call and put prices should be efficiently priced. They should not allow for arbitrage. And if your model captures the true dynamics of the market, then you should be able to find parameters such that your model fits the observed call and put prices on the market. And so you find those parameters by perhaps doing some sort of least square fitting. Okay. Now, this approach has a number of shortcomings. One of the main shortcomings is that you're limited in the scope of models that you can choose from. So typically you're limited to those models for which you can compute prices explicitly, because if you can't do that, then you're going to have to run a Monte Carlo simulation to produce prices, and that would make the calibration process very time intensive. Additionally, because you're sort of limited to a few different sorts of parametric models, what is the one thing we know about all models? Well, we know that those models are wrong, at least in some sense. So it's very unlikely that any model that we choose is going to be able to perfectly fit market data. We might be able to fit the implied volatility smile at a particular maturity, but it's very unlikely that any model is going to be able to fit observed prices at multiple maturities. So we're going to have some error in our model in the sense that the model produced prices will not match the prices that we observe on the market. And lastly, these models typically have to be recalibrated on a daily basis. So if you calibrate your models to observed market prices today, and then you do that calibration procedure again tomorrow, what you'll see is that the parameters of your model have changed. So people have realized that there are these problems with parametric models for quite some time. And so one of the approaches that they have taken to dealing with this is they say, well, let's just work with a non-parametric model. So a non-parametric model might be a model where you just say, look, I'm going to assume that the underlying asset here is just a continuous causative process. Maybe it doesn't jump. Okay. And if you limit yourself to just that amount of information, you probably are not going to be able to come up with unique prices for exotic derivatives, path-dependent derivatives relative to call and put prices. But what you can do is you can come up with some upper and lower bounds. So you could say, well, this path-dependent derivative, so this barrier claim or this variance swap or this volatility swap, should be less than the value of like 5 calls plus 2 puts at different strikes. Okay, so the idea is you're going to say what you can about the prices of path-dependent derivatives relative to call and put prices that can be observed on the market. But you won't be able to come up with sort of unique prices of path-dependent derivatives. And while you may be able to come up with some upper and lower bounds for these path-dependent derivatives, because you're working in this non-parametric setting, it may actually be very difficult for you as a banker or a seller of these derivatives to find a hedging strategy to either super replicate or sub-replicate a financial derivative. And often these bounds that you come up with are too far apart to be used in practice, right? So if the value of a financial derivative is something between $2 and $5, and you have a client saying, how much would you charge for this? Well, you need to give them an actual price. So that's a shortcoming of the non-parametric approach. And what I'm going to talk to you about today is something that falls somewhere in the middle, which is what I have called the semi-parametric approach. And the rough idea, and I'll get into more of the details later on, but the rough idea of this semi-parametric approach is that we're going to impose some structure on the kinds of dynamics that the underlying asset can have. And you'll see when I get into more specific details what that structure is. But we're not going to sort of specify a unique model. So we'll say, well, we're going to put ourselves within a class of models. And by putting ourselves within a class of models, what we're going to be able to do is come up with prices and replication strategies for exotic path-dependent derivatives like barrier claims and volatility claims. We won't be able to say the value of those claims is $1 or $2. But what we will be able to do is say, well, it should be worth this many calls and this many puts, or something like that. Okay. Now, this has a number of advantages compared to the parametric set of models that I talked about initially, because non-parametric models are more flexible. Will be more likely to have it will be more likely that some model within the class of models that we consider fits observed market data. So that's a positive. Secondly, because the pricing and hedging strategies will be given in terms of trading the underlying and liquid European derivatives, we will not have to do any sort of recalibration. And the last advantage is that unlike the non-parametric models, we're going to be able to give unique prices and unique, and robust hedging strategies for these sort of path-dependent derivatives that we're going to be talking about. So that's an overview. Let me,
Matt,
yep, go ahead.
we have a question from the audience. Can I put him on?
Yep, you can.
This is Leon.
Go ahead, Leon.
Uh-oh, did I lose you?
He's got his hand up. Do I have
Sorry.
to let him?
Do you hear me now?
I can, yes.
Yes.
Okay. Hi, Matt. By the way, Matt, I had lunch today with Peter's wife, Carol.
Oh, okay.
Yeah, she said hello to you.
Thank you.
And to you as well, David. And to Zal.
Thank you. Yeah.
Matt, question. Would you characterize, let's say, a generic diffusion process where you have some function of S&T in front of the DT and some function of S&T in front of the DW as a semi-parametric example?
If you're not specifying, yeah, I mean, like if, for example, local volatility, like Dupier's local volatility,
Right.
I would consider that a semi-parametric model because you're not specifying specifically the volatility or the volatility function.
Yeah, because I was just thinking, let's say you said that, this S diffuses with respect to some, drift term A of ST and some vol term sigma of ST, right?
Yeah.
I think that like the variance swap would have some bounds on its price, given the price of plain vanillas, I would think, right? Presumably.
Well, for a variance swap, if you put yourself into
Oh, what am I saying? It's right. Yeah, I mean,
log
it's explicit.
contract.
Yeah, that's a bad example. That's explicit.
But no.
That's a bad example. Yeah,
I understand what you're saying. So that would be one sort of parametric model. I'm going to be talking about a slightly different sort of, a different class of semi-parametric models. But I would consider a local volatility model, such as you described, as a semi-parametric model. Yeah.
I see. Okay, thank you
Is that
very much.
helpful?
Yes, thank you. Appreciate it.
Okay. So let me give you my assumptions to begin with. So I'm going to work in a very classical framework. There's going to be no arbitrage, no transaction costs. And for simplicity, I'm going to assume that the risk-free rate of interest is 0. If I didn't assume that, then I would be working with forward prices rather than the underlying asset price. So S is going to be the value of a risky asset. Think of a stock or an index. X will be the log of S. So I guess I'm going to assume, since I'm defining the log, that the value of S is strictly positive. I don't want to take the log of 0. And in this setting, of course, the value of a put and the value of the call at a given strike K is just going to be the expected value of their payoff, right? So here, E denotes expectation under the market's chosen pricing measure. So I'm assuming that the market, we may be in an incomplete market, but if there's no arbitrage, then the market has chosen some risk neutral pricing measure among many possible pricing measures. So, and I'm going to also assume that a call or a put trades at every single strike from 0 to infinity. Okay, so now that's maybe an assumption that people don't like, but you can always sort of at least fit some parametric curve to observe call and put prices. By the way, quick question, is there any way for me to minimize this bar at the bottom? Because at least for me, it is blocking a lot of my slide.
Your slide is coming out fully to us. I know that might be
Yeah,
difficult for you.
I'm talking about the little bar where you have options like chat and mute and things like that. Well, I'll just keep sort of moving it around. Hope that it doesn't block too much. So anyway, those are my assumptions. All right. Now, let me remind you of a result. Well, hopefully it may be a reminder for some of you. It may not be a reminder for all of you. Peter Carr and Dilip Madan showed in a paper back in the 90s that you can represent a function, any sort of, well, it doesn't necessarily need to be a twice differentiable function. It could be the difference of two convex functions in terms of call and put payoffs. So here I have some function f of s, and the idea is I am writing that as a linear combination of a continuous linear combination of put payoffs and call payoffs. So you can do this with almost any function. And well, if I were to replace this little s with the value of the underlying at maturity and take an expectation, everywhere I see a put payoff, when I take an expectation, I get a put price. And everywhere I see a call payoff, I get a call price. And so the takeaway message here is that I can value, so this thing that I've highlighted on the left is the value of a European claim with the payoff f of s. I can always value that relative to put prices that I can observe on the market and call prices that I can observe on the market. And this is model free. I've not made any assumption about the kinds of processes that the underlying asset S can follow. So this is actually quite a powerful result. Now, in order to value path-dependent derivatives, like volatility swaps, variance swaps, barrier claims, knockout claims, look-back claims, I'm actually going to need to make a few more assumptions about the kinds of processes that the underlying can possibly exhibit. And so my assumptions for the rest of the talk are going to be as follows. I'm going to assume that the dynamics of S are of this form here. So without making any further assumptions, what that means, and by the way, this process here, sigma, is an unspecified process. So the volatility process here is unspecified. This is a Brownian motion under the pricing measure. And if I were not to make any further assumptions on sigma, this actually would encompass every single continuous, strictly positive martingale process that you could write down. But I need to make one more assumption. Well, okay, so I'm going to assume that the volatility process integrated is bounded by some constant C. That actually could be relaxed, but it sort of complicates the technical stuff. It would introduce some technicalities that I don't really want to deal with. So I'm just going to assume that the integrated variance from 0 to t is bounded. But the more important assumption is going to be this one, which is that the this volatility process sigma is going to be independent of the Brownian motion W that drives the sort of the random movement of this underlying S. So that has some consequences. One of the consequences in particular is that if you look at the kinds of implied volatility smiles that this sort of model can produce, those volatility smiles will be symmetric. And of course, if you look at things like the S&P 500, the implied volatility smile is generally not a symmetric smile, but it's more like an asymmetric smirk. So in those markets, this assumption that the volatility process is independent of W may not be ideal. However, I would say two things. So one of them is that I've written a paper on looking at what sorts of errors are actually produced if you make this assumption, price a path-dependent derivative using the methods that I'm going to be talking about, in a scenario in which the underlying volatility process is actually correlated with this Brownian motion. And I've looked at how big the error can be, and for certain volatility derivatives, that error is actually not so large. One other thing that I would add is that you can, and I've done this in a separate paper with Peter and Roger, you could add jumps to this model, and the jumps could introduce an asymmetric implied volatility smile. But at least for this talk, I'm going to be assuming sigma is independent of W, and that means that we're going to have a symmetric implied volatility smile. So what sorts of path-dependent financial derivatives do I want to be able to price and replicate in this setting? There's sort of 4 kinds that I would like to price and replicate. And those 4 are listed here. So first of all, X is the dynamics of X using Ito's lemma are given by the top line here. And the 4 kinds of derivatives that I would like to be able to price and replicate are these 4 here. So this is a European, what I'm going to call a European style claim. And I'm going to be very specific, or I'm going to try and be very careful here in differentiating between a European style claim and a European claim. So European claims are claims whose payoff is just a function of the underlying asset's value at time capital T. A European style claim is going to have a payoff which depends not only on the final value of the underlying, but also its realized quadratic variation. So because the realized quadratic variation comes in there, the European style claim has a path-dependent payoff, whereas the European claim, whose payoff depends just on the final value of X, is a path-independent claim. Okay, so I'll try and be very careful when to differentiate between the two. The reason I talk about European style claims is to differentiate those sorts of path-dependent claims from the other sorts of path-dependent claims, which are going to be knockout style claims. So here, a knockout style claim will be a claim that gets a payoff of this form, so long as I don't hit some barrier prior to time capital T. So here, tau is the first time X will leave some region, which I've called I, some interval I. We're also going to consider knock-in claims. So for a knock-in claim, you'll get this payoff, which I've tried to highlight in yellow here, so long as I actually do hit the barrier prior to time capital T. And I'm also going to talk about rebate claims, where you get some payoff of the realized quadratic variation up until you hit a barrier. Okay, so those are the 4 sorts of claims that I am going to hopefully be able to tell you how to price and replicate in this talk. So let's start with the simplest ones, which are European style claims. Now, rather than tell you how to, well, what we're going to do is we're going to do this in a number of steps. So the main thing that we want to do, or the first thing that we're going to, yep, is there a question? I thought I heard somebody ask a question. Okay. I'm going to price a European style exponential claim. So that's a claim with this sort of payoff. And the reason that I'm going to price that claim, you can kind of look at this and you say to yourself, well, okay, that claim, if I can price and replicate that, then those are sort of like Fourier basis functions. And so if I can price and replicate these exponential European style claims, then I'll be able to price and replicate more complicated claims using by representing functions as their Fourier representation. So, and this was a result that was derived by Peter Carr and Roger Lee. What they showed is that the value of this exponential claim, so that's this thing here, at time tau star. So tau star is basically any stopping time. It could be a fixed time little t. The value of that claim is equal to something that is measurable at time tau star times the value of a European claim. So this is actually a rather remarkable result. It says on the left-hand side, the value of a path-dependent claim is equal to what I have on the right-hand side, which is the value of a path-independent claim. So if somebody told you you could do that, you might be surprised to know that you can actually do that. But in fact, you can. All right. So what is the proof of that? Well, the proof basically follows, this is a very simple proof. I'm going to introduce the filtration generated by this volatility process. So that's this thing in blue here. So if I were to condition on the path of sigma, then we know that the distribution of x is a normally distributed random variable. And the mean of that random variable is -1/2 the realized quadratic variation of x up until time capital T. And the variance is just the realized quadratic variation of x up until time capital T. And so if I were to take the expectation of the payoff of this European style claim, so that's this thing here, if I were to condition on sigma, I can move out the part which is measurable with respect to the sigma algebra generated by sigma. Then I can use the fact that once I've conditioned on sigma, x is a normally distributed random variable, and so I know its characteristic function. And so that is this part here. And then I can use the definition of u, which I have introduced again down here, to go from this line here. And then again, if I were to look at the distribution of x here, conditioned on sigma, that's, again, it's a normally distributed random variable. So going from this line here to this line here is just, again, using the normality of x when I condition on the path of sigma. And then this last line is just removing the conditioning on f of sigma. So it's a very simple proof. It's all algebraic. But again, the takeaway message is the value of a path-dependent claim can now be written as the value of a European path-independent claim. And again, we're going to be using this over and over and over. So try and keep that in memory. Now, of course, if you're a bank, it's not important just to get the price of something. What you actually want to do if you sell a financial derivatives is you would like to know how to replicate that. And you can also replicate these exponential style claims. So how do you do that? Well, I'm going to introduce this process N, which is just defined as this thing here, and Q. So Q is the value of an exponential European claim. And that thing can be synthesized from call and put prices that we can observe on the market using this Carr-Madon formula that I introduced previously. So if you assume that call and put prices trade on the market, then you can trade that asset Q. All right. And the hedging strategy is as follows. I want to hold N European claims, which again is this Q. I want to hold this many shares of the underlying S, and I want to put the remainder of my portfolio, which is this amount here, into bonds. And it turns out that if I do that, this portfolio pi is actually a self-financing portfolio, and it replicates the claim. In other words, the final value of pi is exactly equal to the final payoff of this European style claim. So the proof of that is a little bit more complicated than the proof of just the pricing formula. But basically, the proof is as follows. And I'm going to skip some steps. But so this was the portfolio. The value of the portfolio at time little t is given by this expression here. So I'm just repeating what I told you on the previous page is actually the pricing strategy. And the number, this term here cancels with this term here. So the value of this strategy pi is always nt times qt. Now, if I go to time capital T and I use the definition of nt times qt, I end up with a simplification which shows that, well, the value of this payoff is or this portfolio is exactly the value of the payoff that I'm trying to replicate. Now that shows replication, but it doesn't show that this portfolio pi is self-financing. So in order to do that, all I have to do is I have to take the differential of pi, and I have to show that the change in the value of this portfolio is due only to changes in the value of this underlying Q and changes in the value of this underlying S. And if you go through and you use Ito's lemma and you do some computations, indeed, you do find that the change in the value of pi is just due to changes in the value of Q and changes in the value of S. Okay, so that shows that this is actually, this replication strategy is actually self-financing. I'm not adding or subtracting cash to it out of my pocket, right? So now we've been able to price and replicate these exponential style claims. So what other sorts of claims can we now price and replicate? Well, one of the things that we can price and replicate are power exponential claims. Okay, so this is what I'm calling the payoff here of a power exponential claim. I have powers of x, powers of the realized quadratic variation of x, and also this exponential piece. And the way that we price those things is I note that, well, if I want this power, n powers of x, I can just differentiate with respect to omega n times. And if I want m powers of the realized quadratic variation of x, I can just differentiate with respect to s m times. And so I pull those differentials outside of the expectation here. I know now from the previous result how to relate the value of this exponential style European claim to the value of European style claim to the value of this European claim. And then I can pull these derivatives through. And so what I have is the value of this path-dependent power exponential European style claim is now equal to the value of this European claim. And you can also differentiate the replication strategy with respect to omega and s, and that will give you the replication strategy for pricing and replicating, or for replicating these sorts of power exponential claims. So we can actually go a little bit further and we can sort of replicate a whole variety of, I don't want to say any function, any payoff of x and the realized quadratic variation of x, because there are some integrability constraints. But the basic idea is if you can write a function using its Fourier representation, then you can figure out a pricing and hedging strategy from that Fourier representation as well. So we'll actually see that in action a little bit later on. But that's
Matt?
as much as yes, go ahead.
Sorry, quick question from me. So when you say replicate in this case, are you talking about replicating a path-dependent option with a single European option or with a continuum of European options at different strike prices?
Well, in this case, like let's go back to the exponential one. So the replication strategy here is to hold n, okay, European claims, and the European claim I'm talking about is Q. Okay, so Q is this payoff here, right? So now that's the only claim that I actually need. Now, does that claim trade on the market? In reality, no. However, what I can do if I have a continuum of call and put prices is I can create that claim by holding a basket of call and put prices. So it's not that I have to hold many different claims. This one claim is enough. But of course, if that claim doesn't trade, then I have to synthesize it from call and put prices. Does that make sense?
Yeah, so in practice, if you were to do something like this, you would require, a fairly large option portfolio, right? Long and short puts and calls at different strikes.
Yeah, absolutely. Yeah. You would, I mean, in reality, you would need a continuum of call and put prices.
Right. Trying
I
to
should,
bridge that gap for myself here.
yeah, well, this is a lot of information to digest in one sitting.
Yeah. Okay.
So the other thing I should say is I've talked about, maybe I should have said this right from the get-go. So I introduced this exponential style claim, and here this I, okay, this is imaginary I. So, this payoff is a complex payoff. So when I talk about replicating the payoff or a complex payoff, think about replicating the real part of it and think about replicating the imaginary part of it, because that's what I'm able to do with this sort of thing. Okay, so we're talking about replicating the real and imaginary parts of these sorts of things. Because otherwise you're sort of looking at that and you're saying, well, I don't know any claims in the market that sort of have complex value payoffs, right? Okay, so we've talked about European style claims. Let's now transition and talk about single barrier knock-in claims. So here, I'm gonna define tau L as the first hitting time of X to level L. And for simplicity, I'm gonna assume that L is less than the initial value of X. So that's not strictly necessary. I mean, I could have that level be above X, but you just, change the algebra a little bit. And what I would like to do is I'm going to consider these knock-in style claims. So again, what is the payoff of this thing? Well, if tau L is less than or equal to the maturity date capital T of this option, so in other words, if I hit this barrier prior to time capital T, then when I get to time capital T, I'm going to get a payoff, which is some function phi of the difference of X at time capital T and the time it hits the barrier, and the realized quadratic variation of X between the time it hits the barrier and the time, the maturity date. Now, if I don't hit the barrier prior to time capital T, then the option doesn't knock in and you don't get any payoff. Okay, so these are the kinds of claims that I would like to price, okay? And the way that you can, well, I'm going to talk about replicating. So the way that you can replicate these sorts of claims is as follows. At time 0, in order to replicate a knock-in exponential claim. So this is, again, I'm going to start working with these exponential claims. The way to replicate this knock-in exponential claim is to, at time 0, hold this European claim. So I've defined what that is on the right-hand side. You can see that it's European because only X appears on the right and not the realized quadratic variation of X. So I hold that thing at time 0. And if and when I hit the barrier, this level L, at that point, the option knocks in and it becomes a regular European style exponential claim. And I can price and replicate it using the pricing and replication strategy that I gave you previously for these exponential European style claims. So why does this strategy that I've given you here actually work? Well, it works for the following reasons. We have to imagine two scenarios. The first scenario is that tau L is greater than T. So in other words, I will not hit this barrier L prior to time capital T. Well, if I don't hit the barrier prior to time capital T, then I know that X of T is going to be greater than L. And so because of that, this indicator function and this indicator function over here are both 0. So this European claim that I'm holding in order to replicate the payoff of this knock-in claim is going to be worth 0 at maturity. And of course, the knock-in claim also pays 0 at maturity. So in that sense, it's replicating the payoff in the scenario where the barrier is not hit. Now, what happens if the barrier is hit? Well, if the barrier is hit, in other words, if tau L is less than t, then what you can show is that the value of this European claim that I'm holding at the time I hit the barrier, so I'm taking an expectation condition on the information I have at time tau L, is actually equal to the value of what will be the payoff of this knock-in claim at maturity. So I can trade the portfolio or the value of my claim at the time I hit the barrier for the portfolio pie that now replicates this European exponential claim. Okay, so that's the idea of the replication strategy. Now, what about not an exponential knock-in claim, but instead a claim which pays some fractional power of the realized quadratic variation of x between time tau L and time capital T. So this is of the form of these knock-in style claims that I want to consider, but it's not an exponential one. So if I were to take R as 1/2, then this would be a knock-in volatility swap, okay? And it turns out that the value of that knock-in volatility swap is equal in value to the value of a European claim, which I'm going to call G of X. And G of X is just given by this function of X that I've written on the right-hand side, where psi KIL, this is sort of my notation for psi KI counts for knock-in. It's the payoff of the exponential claim that I gave you, or of the European claim that has the same value as the knock-in exponential claim, which I introduced previously. Okay, so why is it that this function G of X, which I've given here, has the same expectation or the same value as this knock-in style claim? So the reason is as follows. If I want to write the fractional power of V, I have this nice integral representation, which I've written here on the top line. So if I want to look at the value of this knock-in style fractional power of realized quadratic variation, I just use that representation on the top line. I pass this expectation through the integral operator, and then if I look at this thing over here, what I now have is I have two knock-in style exponential claims. So the first knock-in style exponential claim is just the one with this 1 in here. So you can imagine that's e to the 0. And here I have e to the minus z times this realized quadratic variation part of x. And I showed you previously how to relate knock-in exponential style claims to the value of a European claim with this payoff psi ki of x. And so that's all I'm doing, going from this line up here to this line down here. And then I pull this expectation out. And what I'm left with is this G of x, which I gave you previously. So now what does this function G of x actually look like? So what I've plotted on this page is G of log of s. Remember, x is the log of s. So I'm plotting G of log of s as a function of s. This dashed vertical line over here on the right is the level of the barrier. And G here, G of log of s, is the solid line. Okay, so it looks like in order to price a knock-in volatility swap, what I want to do is I want to hold something that kind of looks like a put payoff, although it's not exactly a put payoff, because you can see it sort of curves up here a little bit. But that's the basic idea. I want to hold that until the stock comes down and it hits the barrier of that vertical line. And if it does, then I trade that European claim for the value of the replicating portfolio that will subsequently replicate the European style claims that I now have to price and hedge. And you can see that G is 0 to the right of this line. So if I don't hit the barrier, this European claim that I'm holding doesn't have any payoff at the maturity date. Okay. So that takes care of these knock-in style claims. Now, what about a knockout claim? So I'm going to move on now to single barrier knockout style claims. So tau L is going to be the same thing it was before. It's the first hitting time of level L, and I'm going to assume that L is less than x of 0. And I want to consider a single barrier knockout claim. So that claim will have a payoff which is given by phi of x and the realized quadratic variation of x, so long as tau L is greater than t. In other words, as long as I do not hit the barrier prior to time capital T. If I do hit the barrier prior to time capital T, then the option will pay nothing. All right. So the way that one would replicate such a claim is as follows. I'm going to consider a single barrier knockout claim. And what I should do at time 0 is I want to hold a European style claim. So that's a path dependent claim given with this payoff structure. So this phi KO of L is given by everything I've written here on the right-hand side. Okay. So here I want to be a little bit careful. Okay. What I have to do to replicate this barrier knockout claim is I have to hold a European style claim. And that European style claim, remember, is a dynamic hedge. Okay, it's not this static hedge that I had before for the knock-in style claim. This is a dynamic hedge because I'm replicating this knockout claim with a European style claim. So European style means path dependent. Now, if I do hit the barrier prior to time capital T, it turns out that I can liquidate this position at no cost. All right. So why does this hedge work? Well, this hedge works for the following reason. Again, I'm going to consider the case first where tau L is greater than T. So if tau L is greater than T, meaning I do not hit the barrier prior to time capital T, then I know again that x of T is going to be greater than L. And this European style claim that I'm holding at time 0 has two indicator functions here. Okay. The first indicator function is 1 because x of T is greater than L. The second indicator function is 0. So this second term goes away. And the payoff that I get in that case is phi of x of T and the realized quadratic variation of T. And of course, that's the value of this knockout claim in the case when the barrier is not knocked out. On the other hand, if tau L is less than or equal to T, then what you can show, and it takes a bit of work, but what you can show is that the value of this knockout claim that you're holding at time 0 is equal to 0. And so you can just liquidate the claim at that point, all right, at no cost. So now let's dig a bit further. Okay, remember, I've now related the value of a knockout claim, knockout path-dependent claim, to the value of a European style claim. But, you know, what trades on the market, or what we can synthesize from calls and puts, is a European claim. So what I want to do is I want to relate the value of this knockout claim to the value of a European claim. So I just showed you that the value of a knockout exponential style claim can be written as the difference between two European style claims, which I've written here as H and G, and I've given expressions for what those would be for this particular case. All right. And I want to relate the value of H and the value of G, these two path-dependent claims, to the value of a European path-independent claim. So how do I go about doing that? Well, what I'm going to do is I'm going to focus on this function H. And you can see that it has little h here, okay? Remember, little h here has this indicator function. So that indicator function is basically a Heaviside function. And so because it's 1 if x is greater than L and it's 0 otherwise. So what I'm going to do is I'm going to rewrite that over here. And then on the next line, I'm going to replace h with its Fourier representation. So you can write the Fourier representation of a Heaviside function. And so that's what h hat is. And the reason that I do that is because it takes the x from down here and it puts it up into the exponential. And now if I pass this expectation through the integral, what I'm left with is an expectation of a European style exponential claim, and I can relate the value of that European style exponential claim to a European claim. And then I can pull that expectation out of the integral, and what I'm left with is some function of just x by itself. Okay, so that's the basic idea. So now let's take a look at a specific example. What is the European claim, which I'm calling here f sub n, that replicates a knockout power exponential claim? So here I'm choosing a very particular one. I think I'm choosing a knockout variance swap. So I've taken j to be 0. Oops. Let's see here. Oops. I've taken j here to be 0. I've taken k to be 1. And I've taken p and s to be 0. So what I'm doing is I'm showing you the European claim, or the payoff of the European claim, that has the same value as a knockout variance swap. So you get the payoff of a variance swap if you don't knock out, but if you knock out, you get nothing. And so there's two dashed vertical lines here. I don't know if you can see it. The first dashed line, this is the value of S, or the underline. Yeah. And then the barrier is over here a little bit. Okay. And this right-hand pictures, I've just moved, I've just zoomed in a little bit. So this is the European claim that you would want to hold. Now, of course, if you look on the market, you're not going to be able to buy this European claim. Okay, so it has to be synthesized from call and put prices. The other thing I should mention is this shape will change as the underlying asset moves towards and away from the barrier. So this isn't like the knock-in claim that I talked about originally. The knock-in claim, remember, has a static replication strategy. You just buy a European claim at time 0 and you hold it until the barrier is hit. In this case, it's dynamic hedging. Okay, and you would have to sort of trade different European claims, shuffle around the amount of calls and puts you have in your portfolio. So hedging this knockout claim is a little bit more complicated. Well, I should be honest, quite a bit more complicated than just hedging the knock-in claim. Right, so knockout claims are a bit more difficult. So the last sort of claim that I want to talk about replicating are these rebate claims. So here, tau L again is going to be the first hitting time of X to level L. And here it doesn't actually matter if L is above or below X, the replication strategy is the same. So the idea of these sorts of payoffs is that what you get at the maturity date capital T is the realized quadratic variation of X up until a time it hits this barrier tau L. Okay, so this is the payoff you get at maturity if tau L is less than or capital T, otherwise you get nothing. And the way that you want to replicate this single barrier rebate claim. So here I'm going to consider a single barrier exponential rebate claim, is at time 0, what I want to do is I want to hold this European style claim, and I want to sell one single barrier knockout, which I've highlighted here on the bottom. So I have to hold a European style claim and a knockout style claim. And I've told you how to price and replicate a European style claim and how to replicate a European knockout claim. So why does this replication strategy work? Well, in the case when tau L is greater than T, the rebate claim pays nothing. And of course, the hedging portfolio also plays nothing because what I'm holding is this European style claim and this knockout claim. But in this case, the knockout claim doesn't knock out. So I have the same payoff for both of them. So the payoff is 0 because I'm short the barrier claim and I'm long the European style claim. On the other hand, if tau L is less than or equal to capital T, then what you can show is that the value of this knockout claim, or this European style claim, is equal to the realized quadratic variation of X up until up until the time you hit the barrier, okay, which is what the payoff is. So you replicate the claim whether tau L is greater than or less than or equal to capital T. And again, I've shown you, so remember this replication strategy is I have to hold a European claim and I have to hold a European style knockout claim. And what I would like to do is relate those again to the value of a European claim. And you can do that using the same procedure I did for the knockout claim. And so all I've done is I've skipped the algebra and I've shown you what the prices are of these things, or what the payoff looks like. So I've done two different pictures here. On the left, what I have is you have to imagine the stock is above this barrier, which is this vertical line on the left. And what I'm doing is I'm showing you how the European function F that prices the rebate claim changes as the underlying S moves closer to the barrier. So this dotted line, which is on top, is when the underlying asset is furthest away from the barrier. And as this S moves towards the barrier, the value, or the line moves down. Okay, and that makes sense because if you're close to the barrier, the realized quadratic variation between when you buy the option and when you hit the barrier is going to be smaller. Okay, so if you can imagine, as S moves towards the barrier, the solid line on the left would just move down to 0. All right. And I've also plotted this function F, or the F of log of S, in the case when the barrier is above S. So on the right-hand side, you have to imagine this vertical line is a barrier which is above S. Okay. So because we're coming up on the end here, I think what I'll do is maybe just mention some shortcomings here and stop in case there's any questions. So again, one of the possible shortcomings I mentioned is again that if you're talking about equity options or options on the S&P 500, this assumption that sigma is independent of W implies that you would have a symmetric implied volatility smile, and that's generally not a good assumption for equity options. It's okay for FX options, but for equity options, it's not great. The second possible shortcoming, or I would say limitations of this framework that I've given you, is that S is assumed to be a continuous martingale, and you may be in a situation where you think the underlying S can jump. Okay. What I have done in two other papers with Peter and Roger is we have considered the case in which S is correlated with W, and we're able to price some sorts of path-dependent claims in that scenario. And we also have a paper where we introduce jumps. And either correlation of sigma with W or adding jumps can be a way to introduce jumps into the model. And so if anybody has any questions about those papers, I can answer them in email and point you to those papers. So anyway, I will stop there in the interest of time and ask if there are any questions.
Well, thank you, Matt. That was fantastic. Very interesting presentation. Any questions from the audience? Here we have one here from Leon. Oh, here we go. Go ahead, Leon.
I think maybe that was just from before, but if Leon has another question, happy to take it.
Oh, no, yeah. Do you hear me? You guys hear me now?
Yes.
Yeah. Matt, wonderful talk. I have a question, a very, very basic question. I pardon my ignorance here.
No, that's okay.
Way in the beginning, when you talk about this formula, that is an exponential of both the terminal value of X and the quadratic variation, right? Right. So you alluded to some Fourier series motivation for that particular formula.
Yeah.
My ignorance here is showing, like why I mean, obviously that's just some particular, and omega and S are just numbers, right?
Yeah.
It's just some product of exponentials of both the terminal value and the delivered quadratic variation, right?
Yep.
What's the motivation focusing on that function of x of t and the quadratic variation of x?
Can you ask your question again?
Yeah, I was gonna say, I didn't, you mentioned why the motivation for looking at that particular exponential function
Oh, yeah.
of the terminal value of x and
Yeah,
and there's motivation from Fourier series, right? You said?
Yeah, from Fourier transforms, actually. So I think the easiest way to show you where that is extremely useful is when I talk about these knockout claims. So it's sort of, I mean, the idea is if I can write, subject to integrability conditions and smoothness conditions, I can write any function as its Fourier representation, right? I can write it as the inverse Fourier integral of an exponential, something like this, times its Fourier transforms integrated. Okay, so the place that pops up. So here's one example where that's useful. Okay, here I have this heaviside function. I have x and I have this exponential piece, but here I have this. So if I look at this whole thing, I say, well, that's a European style plane.
Right.
But I don't know how to replicate that thing. I don't know how to represent that as equal in value to just a European plane. And that's the point, right? So what I've done in this particular case is I've said, okay, I'm going to replace the heaviside function with its Fourier representation.
Right.
So now you have to imagine I'm integrating with respect to omega. H has a Fourier representation, which I'm calling h of x. And so this h of x, now I have here an I omega p, sorry, a minus I omega times, oops. That's where this x comes in, So the point is, by writing it as a Fourier representation, I can move this x from down here up into the exponential up there. Now I pass my expectation through. So imagine the expectation hitting this thing I've highlighted in yellow.
Right.
I know how to represent that in terms of
From
a
before,
European plane,
right.
And so that's the whole idea. Is just,
But let's say Matt, I had a claim. Let's add a claim that paid me, for instance, some other function, maybe a linear function of the terminal value of x and the delivered quadratic variation. I have to write that as an exponential of something else. Then I guess is that correct there to be able to?
Well, I mean, like you could take just any function, take a call payoff function.
Right.
There's like a Fourier representation of that payoff. Right. So then you'll have some sort of, you can always, well, it'd be better if I could write, but the idea is you would write the Fourier representation of that function. So when you write the Fourier representation of a function of x, let's say, what you have is an integral f of omega e to the I omega x.
Sure. Right.
Now pass that expectation through.
I got it. Okay. Understood. Yeah. So, but you have multiple, you have infinite number of terms though, of course, right? It's an integral, right? Yeah.
It's an integral, but then you pull that expectation out and what you're left with is just some function of x. As I have down here.
I see what you mean. Okay.
So here I just f of x. What is f of x? Well, it's this function here. So if you can do that function, if you can evaluate that function either analytically or numerically, then you have just a function of x. I mean,
so f could be, let's say, the call payoff for anything very, very simple as well. This will still be true. Yeah, right.
Yep, exactly. The only issue that pops up, and actually it does limit in some sense the scope here, is you take this exponential here and you want to pull it out of this integral. And there are some integrability limitations on that. You can't just do it for any function. There are some functions for which it can't be done. right? Because you're interchanging an integral with an expectation.
Right.
And so there are some limitations. And so actually a lot of the work in this paper is sort of when can you do that? When can you not do that? Right?
Thank you very much.
Matt, I have another question. It's on the practical side because that's where I live.
Okay.
So I remember when I was working at JP Morgan, there was a quant there who claimed that he could replicate these path-dependent claims by having a combination of different European calls and puts at different strikes and times to maturity. I noticed in your paper that you're able to get these nice results with a constant, maturity T. If you added the ability to have options at different strikes and maturities, would you be able to sort of get around this? How should I say, construction of this Fourier element?
That's a very good question. I don't think in general you would be able to remove the need to use these Fourier representations. I think but it is true. I know people have written papers on using options at different maturities to replicate different path-dependent claims. I think actually my office mate and roommate when I was at Princeton, Andrew Papanicolaou, who you guys know.
We do
Right,
know him,
right.
yes.
Yeah. He has some paper, I think, in which he looks at maybe options on the VIX and maybe has some bounds by looking at options trading at different maturities. I'd have to go back and look at that paper. That's the only thing I'm aware of in terms of using options trading at different maturities.
Yeah, I did find this fascinating, but I was puzzled about replicating this,
Well, I
exponential
I don't actually think that that's such an issue. Well, okay. I mean, for example, let's take this knockout plane or this knock-in plane. I mean, if you look at the payoff here, that's not so hard to replicate.
No.
At least very closely, right? So I mean, that's basically hold maybe one or two puts, right? Hold a put with a strike kind of at 90 and maybe add another put with a strike of like 10 or something like that.
Which is probably worth nothing anyway. So I mean, it's
So I mean, it's not so bad. I mean, what you would want to do is you get the shape, and you're going to want some polygon that closely fits the shape, right? Which you could construct out of calls and puts. Now, actually, maybe I should have mentioned this. I have a paper with my colleague here at the University of Washington, Tim Leong, where we address this idea of, all this sort of is based on this Carr-Madon result. So this Carr-Madon result is like, hey, you can represent any function as a linear combination of call and put payoffs, right? And what I work on with Tim is we say, okay, let's suppose you only have a discrete number of strikes, or let's say you're limited to strikes within a particular interval. What are the best strikes to choose, or how many options should you choose for those strikes? And what we do is we solve sort of a least squares optimization problem.
sure.
Well, you could do a least squares optimization, or you can also do a utility optimization. So it's sort of like okay, in a practical scenario, how do you address this?
Unfortunately, I don't know my utility functions, so I'd probably go to least squares.
Yeah. Yep. No, I'm with you on the utility. For a long time, I refused to write any paper on utility functions, and because precisely nobody really knows their utility function. And at least in my own trading, I've not, I can't figure. I do sort of trades by expected return more than anything else. I'm very risk neutral, which is abundantly clear when you see the fluctuations in the value of my crypto portfolio. So.
Well, it's the privilege of youth to have a lower discount for risk. So,
Yeah, I guess so. I guess so.
wow. Any other questions from the audience? Well, thank you, Matt, for a very informative and wide-ranging explanation. This is really really interesting to us, and we hope to stay in touch and yeah, let's not be strangers.
Okay, absolutely. Yeah, it was very nice to get this. It's been a while actually since I've given a talk. This was quite pleasurable. I enjoyed the questions from the audience. So, and feel free to share online. Like I said, I think I signed all the documents needed, so you can feel free to post and share.
Well, as long as you sign the document.
Yeah, I did. I
NYU.
did. All right. Take care.
Thanks, Matt.
Bye-bye.
Bye.